Right. So this is a continuation off of our previous learning goal of determining the location of electrons in an atom. This video involves the fundamental skills of learning about quantum numbers. So quantum numbers involve many of these different sets you see here. So we're going to go at this from a conceptual basis rather than the more specific chemistry and quantum physics standpoint. So we see our most vague quantum number is energy levels. Then we have sublevels, sub meaning below energy levels. Inside sublevels we have orbitals, and then the electrons that travel within those orbitals have specific and particular spins. So you see here that the energy levels specifically talk about the energy an electron has. Sublevels talk about the shape of the path that the electron travels. The orbital talks about the specific path, and then the spin tells whether we have it moving directionally up or down. Because electrons can't travel both in the same direction, they'll repel each other because of the similar charges. So I like to compare this to an address. So I tell my students that this is essentially the address of electrons. So our most vague address involves energy levels. I like to liken that to the state. Sublevels give us the city. We become more and more narrow. We come to the street. And then we find the exact location of an address with the street number. So this is how we narrow it down. Energy levels are very vague. Break down into city, street, and then street number. So our first quantum number is our principal quantum number. That is also known as energy level or energy shell. So those are used interchangeably. We represent them with the letter N. So anytime you see the letter N, N equals, we see it right here on this picture, N equals 1. We're talking about the first energy level or the first principal quantum number. And as I mentioned previously, we're talking about the energy of an electron or its size. So Bohr was the one who discovered and coined the idea of principal quantum numbers and energy levels. He basically said that electrons travel in these orbits around the nucleus at varying sizes or energies away from the nucleus. So we always reference an energy level farthest away from the nucleus as at a higher energy level, and that's because they have more energy than an electron here at a lower energy level. So energy increases as you move outward from the nucleus. Now electrons, we talk about quantum numbers from the standpoint that at particles this size, they no longer obey classical physics and classical motion according to Newton's laws. So we start talking about these small particles traveling both like waves and matter, or energy and matter. So these electrons can absorb energy and jump energy levels. So go from here, from 1 to energy level 2. So this absorption is absorption of a quanta of energy. An electron here in energy level 4 can fall back to energy level 2. So an electron orbiting here in the 4th energy level can fall back. And this results in an emission or release of energy. So this release is a photon. So in this case, our jump from 1 to 2 absorbs energy. Energy increases. From 4 to 2, we have a release of energy as a photon. Moving on, getting more specific, the angular quantum number is the fancy way to say sublevel or subshell. So this is smaller than an energy level, smaller than a shell. So I like to have my students remember that go S with shape. So we're talking about the shape of an orbital's or an electron's path or electron's orbital. So the formal definitions of the 4 shapes we see are sharp, principal, diffuse, and finite. But I help my students remember this by saying S is spherical in shape, P is dumbbell shape, D is cloverleaf, and F is funky. So sphere, dumbbell, and cloverleaf, those are pretty accepted. I like to call the F orbitals funky shape because they come in all different shapes than you may be used to. Don't confuse P and dumbbell and D with dumbbell. So D is cloverleaf, P is dumbbell. Get those two separated from one another. So we're basically saying that if we were to track an electron within this cloud right here, the way it moves, it's eventually going to be mapped out to a spherical shape. Or the way the electron moves here is going to be in this figure 8 pattern, eventually filling up this whole space. Moving on, we are getting more and more specific, so now we're in specific orbitals. So we have our magnetic quantum number, and we're talking about the orientation or space that an orbital has in a three-dimensional plane. So here we have, again, the S sublevel, the P sublevel, the D sublevel, and the F sublevel. So S is our first sublevel, P second, D third, F fourth. So as we saw from the previous slide, we have these four shapes, and it's important to remember that in these four shapes we have different numbers of orbitals. So right here, these are all something you just simply have to remember. What I recommend my students do is start at S, because S is the simplest, the spherical, and just count up by odd numbers, 1, 3, 5, 7, and that has your basis covered for S, P, D, and F. So again, we have S, P, D, and F. And you'll notice to the side, next to all these orbitals, we have numbers of electrons. So S has only one path, one orientation. Each orientation holds 2 electrons. So 2 electrons times one path gives us 2 total in that sublevel. So this is electrons in a sublevel. Here, each of these paths, we have 3 orbitals, 3 paths. Each holds 2 electrons. So that means 3 times 2 in each gives us 6 total electrons. So this point right here, that 2 electrons fit in a single orbital, is very important to remember. So that's how we get 2 fitting in S, 6 in P, 10 in D because there are 5 orbitals here, and 14 in F because there are 7. Now, sometimes you'll be asked to say how many electrons are in a 5p sublevel versus a 3p sublevel. Remember, this number right here is our more general part of our address. So this deals with our energy level. Here is our sublevel. So the number here is just saying that the 3p sublevel has less energy than a 5p sublevel because of the difference in energy levels. But because they're both the same sublevel, we can see that they both fit the same maximum number of electrons, so 6. So the answer to these, they both fit identically 6 electrons at most. Now, the quantum number formulas that you'll have to remember is that if we're ever asked to find the maximum number of electrons in an energy level, that is governed by the formula 2n squared. And then the next one is if we're ever asked to find the maximum orbitals in an energy level, that's governed by n squared. So we can write out this table like this. If we have one energy level here, we know we have one S sublevel. So the number of energy levels matches the number of sublevels. So we know that 2 electrons fit here in the S sublevel. So if we put in 1 for 2n squared, 2 times 1 squared gives us 2 maximum electrons. If we go here to the second energy level, we now have 2 sublevels, S and P. S still fits 2. And as we learned previously, there are 6 maximum electrons that fit in P. 2 plus 6 is 8. If you take this, plug it in here, 2 times 2 squared gives us our 8 total electrons. We'll go one more energy level further. The third energy level has S, P, D sublevels. We hold 2, 6, and 10 total electrons. So again, 3 squared is 9, times 2 is 18. 2 plus 6 is 8, plus 10 is 18. So these formulas help to simplify working all of these out. And if we wanted to extrapolate and add on our number of orbitals, we can see here that S has only 1 orbital, S here has 1, P has 3, 1, 3, and 7. Oops, 5. So 1 squared, according to this, finding maximum orbitals in the first energy level, 1 squared is 1. 2 squared, maximum orbitals in the second energy level is 4. 1 plus 3 is 4. Maximum orbitals in the third, 3 squared is 9. 1 plus 3 plus 5 is 9 orbitals. So that's how you apply these formulas to your quantum numbers. So I hope that this helped you in understanding the difference between energy levels, sublevels, orbitals, and spin. And hopefully you now have a better conceptual understanding of how quantum numbers work in determining the location of an electron.